All right, we're in chapter 1 on section 3 on linear regression. So we're going to do mathematical modeling, which is the process of using mathematics to solve real-world problems. There are 3 steps in this process. First, we have to construct the mathematical model for the real-world problem. Then we have to solve that mathematical model. And finally, we have to interpret the solution to the mathematical model in the terms of the original real-world problem. All right, so here's our cycle. So we have a real-world problem. Then we have to construct the mathematical model. Then once we get that, then we have to solve that model and get a mathematical solution. And then we have to interpret it back into what the real world problem was asking for. So that's kind of how we have to do this in a whole cycle. We start with a problem, we make a model, we solve the model, and then we interpret it. And so our answer is going to have that real world problem answer based on all the model as well as the solution. Now, in complex problems, the cycle may require repeating to obtain that required information about the real world problem. So it doesn't always happen the first time, so sometimes you have to repeat it to get that required information. And linear and quadratic functions can be used to construct mathematical models of real world problems. Those are the 2 easiest ones. There's other ones out there, but those are the 2 nice ones. And since we're in linear modeling in this chapter, linear is probably going to be the way we're going to go. And so for slope as a rate of change, if x and y are related by the equation y equals mx plus b, where m and b are constants with m not equal to 0, then x and y are linearly related. Now, if we have the 2 points, x1, y1, and x2, y2, and they're 2 distinct points on the line, then we found the slope in 1.2 as a change in y over the change in x, and that was rise over run. Now, we can say this is actually called a rate of change. And so our ratio, which we said was the change in y and change of x, is called the rate of change of y with respect to x. Okay, so now we've come up with a rate of a change kind of thing. So we started with being slope, now we're converting it into calling it the rate of change. Now, since the slope of the line is unique, the rate of change of 2 linearly related variables is constant. Now, if the relationship between x and y is not linear, then this ratio is called the average rate of change of y with respect to x. Okay. Now, so let's look at some examples of rate of change. Measurements such as miles per hour, revolutions per minute, price per pound, passengers per plane, and so on, all examples of rates of change because we have our rate and that's our change. Our rate, our change, our rate, our change. And so we can see that those are different rates of change. Now, each of these measurements are ratios of differences in 2 quantities. For example, if a car passes a mile marker 1:20 at 1 p.m. and passes a mile marker 3:30 at 4 p.m., find the rate of change in distance over time. Well, basically what we have to do is we have to do the calculation, change in y over change in x and all that good stuff. And so what we're going to do is we're going to say, okay, well, what is our change in miles? Well, we've gone 330 minus 220, so we'll have 330 minus 120, I guess, instead of that. And that's going to give us, what, 210 miles. And the time, we went 4 o'clock to 1 o'clock, so 4 minus 1, so that's going to be 3 hours. And so our rate of change then is going to be how many miles did we go per hour? Well, we went 210 miles in 3 hours, or if we divide that out, we're going to get 70 miles per hour. And so our rate of change is 70 miles per hour. That's how fast we were going in that case. So that's our rate of change over that distance. All right, what if we have a university club sells custom printed t-shirts? The cost function that gives total cost C of x in dollars as a function of the number of t-shirts they have printed is given as C of x equals 250 plus 4.5x. So this one, they put the b first and our slope here. So you kind of went backwards at what we're normally used to because we usually do y equals mx plus b, but you can write it in any order, so that's okay. Now, give the slope of this cost function and interpret the meaning of this slope in the context of the problem. All right, well, our slope is 450, so, oops, we have, in this case, the slope is equal to 4.50. And what does that mean? Well, in this case, the x is in dollars as a function of the number of t-shirts. So t-shirts is going to be X. And so what we can say is whenever one t-shirt, additional t-shirt is printed, the total cost of printing increases by, well, it increases by $4.50. Okay. Now, this has a special name, given the cost function and interpret the meaning of the slope and context of the problem. This is actually a marginal cost. So the marginal cost is going to be what this is represented by in this case. So I'll let you read more into that, but that's what the meaning of this is for that. So the rate of change is it's going up by $4.50 for every t-shirt added. So each additional t-shirt that's printed, the total cost of printing is increasing by $4.50. And again, it's all based on that that slope there. Now, what if we have a 100-pound cargo of delicate electronic equipment that's dropped with a parachute from an altitude of 2,880 feet and lands 200 seconds later? All right. So we want to find a linear model relating altitude in feet and time in the air in seconds, and how fast is that cargo moving when it lands? All right. So what do we have to do? Well, if we're going to call A as in feet and time is there, so we're going to look for A of t is equal to what? Well, that's going to be some m of t plus b, okay? So what numbers do we know? Well, it starts at an altitude of 2880. So at time 0, it's at 2880. And the other number we know is, and lands 200 seconds later. So at time 200, we are at 0 feet, correct? Okay, so we have to find the slope of this. So the slope is going to be what? Well, the slope is going to be the change in altitude over the change in time. So let's take 2880 minus 0 over 0 minus 200. And again, we have to do, if this is x1, y1, this is x2, y2, or if this is x1, y1, and then this is x2, y2. So we have to, be consistent however we want to do it. So if we say this is top one, and this is usually how it is I'm going to take the large one, usually minus smaller first on top, and then whatever happens on the bottom. So what do we get? We get 2880 over a negative 200. And if we divide that out, let's see, that's going to be 2880 divided by 200. So that's going to be 14.4. And so that's going to be equal to negative 14.4. And what is our units going to be? Well, it's going to be per second. So it's dropping 14.4 feet per second, basically. Okay. So now we need to get the model here. So the equation, let's do y minus y1, in this case is 0, just because that's makes it easy, is equal to the slope, which is a negative 14.4 times x minus x1, which was going to be our 200. Where am I letting thing go? And so this is going to be, well, that cancels out. And so we get y is equal to a negative 14.4x plus 14.4 times 200. It better give us a 2880, which it does. And so that is going to be our equation of our line. And if we put that back into this type of function, it's actually going to be a of t is equal to minus 14.4 t plus 2800, and this is going to give us feet. Okay, that's going to be our units there. Okay, how fast is the cargo moving when it lands? All right, so basically what's happening is we know the rate of descent is it's going down at 14.4 feet per second. So, we're dropping at the rate of change is 14.4 feet per second. Well, how fast is it moving? Well, when we do a speed, we want to know just the positive number. So our speed in this case for B is just going to be the absolute value of that. And so it's going to be going 14.4 feet per second. Okay. So, it's based on going from high to low, but we're not worried about the sign in the actual how fast it's going. So we take the absolute value of that and we get our 14.4 feet per second. All right, so let's stop there and we'll come back with some more.